Great. Oh, sorry, I put the joint width in the wrong spot here. Thank you. Oops. Goodness. Thank you for the invitation and for putting this conference together. So the goal of the talk today so I want to talk about the Carlsson-Mellit algebras AQ, and AQ was sort of commonly called AQ and AQT. I'd like to give a skein theoretic interpretation of them, so I'll draw pictures. So basically, I'd like to reinvent those algebras or some versions of those algebras using pictures. And then these pictures will be sort of interpreted in the world of Soergel bimodules. This will give a kind of a categorical analog of the algebra AQT. Okay, so to begin with, I just want to talk about something very elementary. So how interesting structures can be presented graphically, just to get us kind of in the mood for what's going to happen later. So this is all hopefully familiar to everyone, the symmetric group algebra. A permutation could be denoted diagrammatically just by a string diagram like so. Symmetric group algebra is the formal span of such diagrams, mod relations. The relations are homotopies, so like, and you know, so for example, that's an embedding of two arcs in the plane, and as such, it's homotopic to this, or sorry, it's an immersion of two arcs in the plane, and as such, it's homotopic to that, and so on. So the symmetric group can be thought of as linear combinations of diagrams and mod relations in the sort of traditional way. Multiplication in the symmetric group algebra is then interpreted diagrammatically as vertical stacking. This is not the only sort of construction that we'll want to consider. So there's also things you can do to an algebra, like consider Hochschild homology. This is HH lower 0 of an algebra is defined to be that algebra modulo commutators, modulo the vector space spanned by commutators. So diagrammatically, we should imagine, so we're kind of identifying left multiplication with right multiplication, which diagrammatically means identifying top multiplication with bottom multiplication. So now instead of drawing our diagrams in a rectangle, we'll draw our diagrams in a rectangle with edge identification. So we'll identify the top edge with the bottom edge. So that is this annulus we see pictured. And then Hochschild homology of the symmetric group algebra can be thought of as a span of string diagrams drawn in an annulus mod, again, the same sort of relations, homotopies and such. Okay, so a priori, this is just a vector space, or maybe a family of vector spaces, one for each n. But the observation is that if you take the direct sum over all n, you actually get an algebra. So for instance, and so from this point forward, I won't draw the entire annulus. I'll just kind of draw the puncture of the annulus as a little circle in the middle of all of my diagrams. Okay, so the multiplication is given a diagram drawn in this, and instead of an annulus, I guess I'm working in the punctured plane minus an open disk or something. So anyway, so if we have one diagram in this punctured plane and another diagram in the punctured plane, their product is given by sort of concentric union. So you sort of expand, say, the first factor, and you lay it on top of the second factor. So this is the product in this algebra. Turns out it's commutative because of this, we're modding out by the homotopy relation. Oh, I see some. Okay, cool.
Side chat.
I see, side chat. Yeah, I guess somebody will let me know if there's something I can answer. Okay, this algebra, this commutative algebra is in fact isomorphic to a polynomial ring and infinitely many variables. So we have this fact. So the direct sum over all n's of these string diagrams in the annulus. So isomorphic to this algebra, polynomial ring and these generators pi, where pn is the dude that loops n times around the puncture and comes back to itself. Again, because I'm modding out by homotopy, the only relevant information here is the number of connected components, 1, and the number of times it winds around the puncture, which I guess is supposed to be n in this. Just as an example of how one could write an arbitrary diagram as a monomial in this isomorphism. So again, as I said, that the relevant information is the number of components and then the number of times each component winds around the whole of the annuals. So if we start with the first sort of component, and anyway, this is the kind of skill that'll be useful later. So let me go through it in detail. So our first component, this purple component, winds around the whole of the annulus twice. So that's going to give us a factor of p1 squared, or sorry, p2. Our second component, if you follow it around, also winds around the whole of the annulus twice, so that contributes another factor of p2. And so this diagram, represents this monomial p2 squared. Okay, so in this way, permutation, yeah, and this is the sort of standard fact that the, I don't know, representation ring or whatever of the symmetric group algebras give a copy of this ring of symmetric functions. So if you like, you can think of this as a copy of the ring of symmetric functions, where the symbol pi denotes the ith power sum symmetric function. I won't write that, but this is kind of a well-known standard fact. Okay, so this is an example of the sort of thing that maybe everyone has seen before, we're all comfortable with. It's no surprises quite yet. There's something slightly more interesting that you can do, which is instead of considering Hochschild homology of the algebra, the symmetric group algebra, you can consider sort of relative versions of that. So instead of drawing our diagrams in the, well, I guess I'd like to consider such diagrams, where I take symmetric group, I take string diagrams representing permutations, and I draw them in some hybrid where I still have some boundary points that I leave open and sort of kind of unglued. But then I take the last m of them and I glue them together around this puncture. So I get a 2-parameter family of vector spaces. So n here records the number of points which meet the boundary, the top and bottom boundary of the rectangle. And m denotes the number of strands which are connected across the whole of that, across the puncture. And d is a diagram or a linear combination of diagrams representing a permutation in Sn plus m. Okay, so instead of connecting up all the strands to get a diagram drawn in the annulus, I can connect up some of the strands to get a diagram drawn in this sort of hybrid guy. Algebraically, what's going on is I'm considering Hochschild homology of, okay, so I have the algebra, symmetric group algebra on m letters, and here I'm considering this guy as a bimodule for that algebra, where the left and right multiplications are given by, so given a permutation on m strands, I sort of adjoin n parallel strands off to the left, and I view this guy as a bimodule. I view this guy as a bimodule over this algebra via left and right multiplication by such diagrams. And so sort of technically speaking, what I've done is taken sort of some version of Hochschild homology with coefficients and described it diagrammatically in this way. Okay, so what I want to do is sort of describe various algebras which act on such spaces. I'll describe kind of a Heck algebra version of this, not a symmetric group algebra version of this. Oh, sorry, I'm getting ahead of myself. This is actually not the vector space I want to consider. I'd like to symmetrize the bottom n strands. So here's this auxiliary space V m n m tilde. I'd like to consider this subspace of that guy consisting of, it's a subspace where I symmetrize the bottom left n strands. And again, I mod out by the same homotopy relation as we've seen. Where this little symbol here, this rectangle, denotes the symmetrizing idempotent. So this is the sum of all permutations divided by n factorial. Okay, now size-wise, this vector space, if you add up all of these vector spaces as n and m vary. Oh, sorry, I want to fix n and take the direct sum over all m's. So we see that v, so when n is 0, we recover the vector space from a moment ago. But in general, for general m's, if we leave some kind of boundary points unglued, we get this polynomial ring, extra factor of this polynomial ring and y's. And the way this works, this will be sort of a useful picture to have in mind. The way this works is, again, we're interested in kind of decomposing such a diagram into its components and asking how many times do those components wind around the whole of the annulus. So for example, here's our first component. It winds around the annulus 0 times. So that's going to give us a y1 to the power 0. Our next component winds around the whole twice before it meets its demise at the symmetrizer. So that's going to give us a y2 to the power 2. Our third component winds around the puncture once before it hits the symmetrizer. And then we have one more component which is sort of yet unaccounted for, which is here. It doesn't meet the symmetrizer at all. It's this independent little thing. And that contributes a copy of P1 because it winds around the annulus once, or the whole once. Okay, so in this way, diagrams give us monomials, and if you think about it, such diagrams form a basis, I guess, I mean, modulo the fact that the symmetrizer eats crossings. Okay, so this is a diagrammatic definition of a vector space, and in fact, we can do more than that. We can sort of define interesting operators acting on these vector spaces. So again, this is all supposed to be motivation for a story that will deform and then categorify in a second. So just bear with me for one moment longer. What kinds of operators, what kinds of algebras can we define acting on this big direct sum? Well, we have multiplication operators given so we can kind of fiddle with stuff on the top boundary. Given a symmetric group element, we can kind of stack it on top. That gives us an action of a symmetric group. More generally, if we have any element of this algebra which centralizes the copy of symmetric group algebra on m letters, then we can insert him we can kind of like multiply there. Okay, so this is a well-defined operation because as is well known, the center of an algebra acts on its cocenter being this algebra mod commutators. And this is a relative version of that fact. You know, the centralizer of a subalgebra will act on the kind of co-centralizer of that algebra. Anyway, you need to check that this respects the relation of left, identifying left and right multiplication by elements of CSM. And that's the same thing as centralizing elements of CSM. Okay, so we have these multiplication operators and two more important guys called the raising and lowering operator. So given a diagram symmetrized at the bottom, you can kind of add a strand and then symmetrize with respect to the larger number of strands here. So that's the raising operator that I'm calling D+, and the lowering operator grabs the rightmost free strand and connects him to his partner below so on the other side of the annulus, okay? So these raising and lowering operators, and the whole point is this required very little effort, and if you wanted to, as an exercise, you could kind of at home, at your desk, whatever, you can figure out relations satisfied by these operators. And the point is you get something interesting with sort of very little effort. So what I'd like to do is explain how the very same pictures describe an act, well, in fact, sort of literally these pictures reinterpreted in the sort of replacing the symmetric group algebras with Hecke algebras gives us this Carlsson-Mellit algebra. Okay, so let me tell you roughly what is the Carlsson-Mellit algebra. This what they call a dict path algebra or the double dict path algebra. So there's two such algebras. The first is, I won't explicitly write the relations here because I don't think it's super enlightening. But roughly what the algebra is so you consider the following quivers. You have a vertex for each non-negative integer. You have a path which increases, sort of moves you from one vertex to the right. You have another path which moves you from each vertex to the left. And then you have various loops. So so in general, yeah, anyway, so you have loops labeled by these symbols y1 up to yn and t1 up to tn minus 1. So for example, at the vertex labeled 3, we have loops y1, y2, y3, and t1, t2. So you consider the path algebra of this quiver, mod a bunch of relations. So the relations are numerous, and I'm not going to write them, but one thing I will say is that the y's and the t's individually satisfy the affine Hecke algebra relations. So the t's satisfy Hecke algebra relations, and the y's commute amongst themselves and have certain commutation relations with the t's. That describes basically the polynomial representation of Hecke algebra, of the Hecke algebra. So the goal, as I want to emphasize, will be to reinvent this algebra. So I actually don't need to state the relations yet. I'll reinvent the relations in a certain sense by drawing certain pictures and then asking how the pictures are related. This doubled dict path algebra is the same sort of thing, except now we have two different kinds of raising operators. We have a d plus and a d plus star. And we have two different kinds of polynomial generators, y and y star. Okay. Again, you mod up by a bunch of relations, which I'm not going to write down. We will see a handful of what these relations look like graphically in a second. Okay, so the whole idea is to reinvent these algebras using Hecke algebra diagrammatics, similar to the symmetric group diagrammatics that we started with. And as a caveat, I should just say that I'm going to, for a moment, I'm going to avoid the letters Q and T and replace them with this neutral thing that I'm going to call eta. So this is like not a standard way of denoting these algebras, but I feel like the letter Q is a little bit loaded, and I don't know. So we'll replace the letter Q with the letter eta squared and the letter T with eta to the minus 2. So in particular, we don't actually have an interpretation of the full algebra AQT, but we only have an interpretation of its specialization where T is Q inverse. So this is still a work in progress. But anyway, so that's the goal. So I have to describe Hecke algebra diagrammatics, and then I have to describe the sort of graphical operators that recover these Carlsson-Mellit relations, operators and relations. So the Hecke algebra diagrammatically is, so instead of taking string diagrams, which represent permutations, we take the break group. So we take, formal intercombination, just to remind everyone who may not be familiar, we take formal intercombinations of braids with n strands. Mod, we have the braid relations, which are the usual isotopy relations for braids. And one more relation, this quadratic, with this relation, which I'll write here in the following way. So you can exchange a positive crossing with a negative crossing at the expense of this smoothing. Okay, and we make all of the same definitions as we had before. I'm not even going to bother inventing different notation for them. So we consider all such diagrams, braids, in the rectangle where we identify, we allow braids to slide from this sort of location to that sort of location. So we'll draw our braid diagrams in a punctured rectangle and modify the exact same relations. So the braid relations and also this skein relation, this thing that we call a skein relation. So that's V and M tilde. We don't actually want to consider this thing, it is too big. So we symmetrize in the bottom left. So we consider the subspace or whatever spanned by such guys, where now we have to interpret this box as the symmetrizing idempotent in Hecke algebra. So what that is some formal linear combination of braids. So for each permutation, you look at the positive braid lift of that permutation, weighted by some power of eta, that's the length of the permutation, and normalized by this sort of n factorial, quantum n factorial. Okay. So this is the usual symmetrizing idempotent, and we do the usual thing. Aha, wait, no, did I? Damn it. Okay, anyway. All right, so at this point, I'm ready to define the sort of skein theoretic versions of the operators d plus and d minus. So we have the raising and operating, we have the raising and lowering operators like we had before. So I want to interpret all of the generators in this Carlsson-Mellit algebra diagrammatically. So, so what this means is we have the loops T1 up to Tn minus 1 acting on so if you fix n and let m vary, these operators will act there, these operators will also act there. And then we have the raising and lowering operators that either increase n or decrease n. Okay, so what I'd like to do is just give you pictures for these things. We'll state some relations, and then I will move on to trying to understand their categorification in the world of circle bimodules. Okay, so the operators Ti, they act, so if you remember, so our vector space V N M is the span of braid diagrams mod a bunch of relations, and we can kind of fiddle with stuff on the top left. We can place braids on the top left, and that describes an action of the Hecke algebra Hn on the top left. So in fact, Ti is interpreted as the positive generator. So it's the positive crossing between strands I and I plus 1. And this acts by, so in fact, the whole Hecke algebra Hn acts on Vnm by the same formula that we had a moment ago.
There's a question from Ben in the chat.
Sure.
Does d minus raise m by 1 instead of subtracting 1 off of n?
D minus subtracts 1 from n and donates it to m. But of course it.
Oh right, I didn't notice the direct sum. Sorry.
Yeah, no, you were good. Yeah, so the Hecke algebra Hn acts by left multiplication. So in particular, the operators Ti act. Sorry for the sloppiness of my picture. So those are somewhat boring. The operators yi are a bit interesting, so I'll try to draw them carefully. So if your input is a diagram, so here what n is 3 and m is 2, your output has been pointed out. Your output will have, oh sorry, I'm getting ahead of myself again. What y does, okay. It grabs the ith strand, winds it around the whole of the annulus, passes under all those guys, and restores him to his original position. Making all these crossings are positive, and if you, all the crossings are, let me make sure that I didn't make a typo here, I'm sorry. Yeah, so that should be right. Okay, so yi basically grabs the ith strand, here I haven't drawn any strands, I've only drawn 3 of them, but it grabs the ith strand and winds him around the whole of the annulus and then restores him to his original position. D plus, this raising operator, does the same thing that I indicated with the earlier pictures. So if you have a diagram which is, symmetrized on below, you add a strand, symmetrized with respect to the bigger idempotence. So that's your raising operator, your lowering operator, and and your lowering operator does the following. Okay, so again, you have a diagram which is sort of symmetrized below. And the lowering operator just grabs the rightmost free strand and connects it to the bottom. Okay, so these are the operators and the kinds of relations they satisfy. So just to kind of give you a taste of the relations these satisfy. So the most interesting relations are things involving d plus and d minus. So for example, so d plus squared. So he likes to absorb crossings T1. So a picture for this relation is, so d plus squared is the operator that takes a diagram. And let me cannibalize an earlier picture. So d plus squared adds a pair of strands to the left and then symmetrizes. And further, sort of following that with a T1, and because this is the symmetrizing idempotent, that means it's an it absorbs all the braids up to a appropriate scalar. In this case, the scalar is just eta. Okay, so doing a pair of d pluses, so doing d1 d plus squared is the same thing as doing eta d plus squared. Okay, so those are kind of relations like this. There's another very similar such relation, which is like a d minus squared preceded by a dn minus 1. So the picture for that would be something like you draw your diagram. Let's say n is 4. So you apply d tn minus 1, and then a pair of d minuses. So this is so that gives you such a diagram, and then using isotopy, this crossing can be slid around and observed by the symmetrizer. So you get relations like this. There's a most interesting relation that I want to sort of state before we start talking about how to categorify these things.
Perhaps we should just take a short break.
Yeah, we have a break, don't we? Okay, yeah, this is a good time to take a break.
Okay.
Do people typically ask questions during the break?
Sometimes.
Sometimes? Okay.
I mean, if you need a break, obviously you should take one.
I'm good.
So if you don't put the symmetrizer on the bottom, what kind of module and what kind of algebra do you get?
That's a good question. I mean, yeah, I mean, the short answer is I don't know. I wouldn't really even know how to compute the size of such a thing. You know, it's like compute the dimension of that object. I haven't thought about it. Yeah, I mean, so obviously, so this vector space that we defined was sort of tailor-made to recover what Carlsson-Mellit do. So that I guess I didn't write this, but the polynomial representations of these algebras, the size of these things is so you take. So your ring of functions is now rational functions in some parameter. Anyway, so this was tailor-made to get the sort of right dimension to be the polynomial representation of the Carlsson-Mellit algebras. And I don't know what you get if you remove the symmetrizer. Do you know?
I don't know. I mean, it looks similar to Monica's talk from yesterday. I don't know if you've been there, but like it's kind of skein of thickened cylinder where you have like allow some points on the boundary on the top, points on the boundary on the bottom, and like wrap around some number of times and like whatever you get there.
You get like some Taha picture.
But why don't you just add a finite Hecke algebra for each n, so that you have exactly what you've written there with the y's and then the p's, and then put in the middle some tw's and sum over w, so that you have a finite Hecke algebra for each n.
I'm not sure I followed.
Well, if I had a PBW type thing with y's on the left and p's on the right, and then I put the span of the TWs for W in the symmetric group Sn in the middle. So the effect of your symmetrizer is to kill all those TWs. So if you didn't have the symmetrizer, I think the TWs would still live.
Oh, I see what you're saying. So this would be the size of, this would be the size of it. That would be the
Yeah.
vector space.
That's my guess. Yeah.
Yeah, that's probably a good guess.
Okay, I think now is probably a good time to
Okay.
come back.
Okay, thanks. So there's one, yeah, okay, so there's one kind of relation that I do want to, sorry, I lost my place. There's one relation that I kind of want to say a little bit about before we move on. So there's a linear relation. So for the symmetrizing idempotents, there's a linear relation that relates sort of the symmetrizer on n-1 strands with the symmetrizer on n strands. So there's a linear relation, the details of which are not super important, but there's a linear relation between the symmetrizer on, say, n strands and the symmetrizer on n-1 strands, and a sort of sandwich where you have crossing in the middle. And let me actually, okay, so there's a linear relation between these three Heck algebra elements. So by kind of viewing all of this in the presence of some other braid, you see there's a linear relation between these idempotents. So there's a linear relation between the symmetrizer on n strands.
Sorry, is that middle long cycle supposed to be going the other way?
Sorry, yeah. Yes, thank you. Actually, I think I did want that one to be going. What am I doing? So this is fine. Yeah, so there's a linear relation between these three elements. Which in the end gives a sort of, gives a relation of the following type. So there's a d plus and d minus. Again, so up to scalars. So what I've written is sort of not literally true, but there's a certain commutation relation between d plus and d minus. Of the following form. So if you take your diagram D, grab the rightmost free strand and wind it around, put it in position 1. And the reason, anyway, so that the reason for this is something like, so D plus D minus of your diagram okay, so D minus first grabs the rightmost free strand and connects it to the bottom. Following that with D plus. And if you remember, D was supposed to already be symmetrized. So there's secretly, even if I didn't write it, there was secretly supposed to be a symmetrizer there. This is supposed to be compared with D minus of D plus of your diagram. So that's this sort of picture, you do d plus, and then you do d minus. And the whole point is there's a linear relation between this diagram, and this diagram. So this is a sort of, anyway, this just hopefully gives you the flavor of how you might discover relations in the algebra AQT and how they come from skein theory and stuff like this. Okay, I haven't been precise enough with normalization to tell you the relation exactly, but this is something that anyone here can figure out. I mean, anyway, you have to know how you have to know exactly what this linear relation looks like, and that's an exercise. Anyway, that's a pretty easy exercise. Okay, so this is all I want to say about Heck algebra stuff for now. I'd like to talk about the categorification. So there's this whole other part of the story, which is this doubled algebra, AQT, that I will possibly draw pictures for at the end, but so I don't run out of time, let me talk about Soergel bimodules and how to categorify this story. Okay. So there's a category called the category Soergel bimodules, which is a categorical analog of the Heck algebra. So this is a monodal category, so it has a notion of tensor product. It is an additive category, so it has a notion of direct sum. And it's a graded category, so it has a notion of gradient shift. Tensor product, direct sum, and gradient shift. And altogether, these form categorical analogues of the multiplication in Heck algebras, addition in Heck algebras, and then the operator of multiplication by whatever parameter, Q or eta or whatever you want to call it. So this thing admits a diagrammatic presentation due to, in type A is due to Ben Elias and Kovanov. And in other types is Ben Elias and Jordy Williamson. So there's this diagrammatic version of the category of Soergel bimodules. The objects are sequences. So there's sort of formal things called Bott-Samuelson sequences. So you take let me write it this way. So just like an element of the Heck algebra could be thought of as a, formally generated by these TIs, this category is formally generated by BIs, where each one of these guys is a simple reflection. Simple transposition in the symmetric group. And typically, each simple transposition is indicated by drawing a color. So for example, if n is 4, or let's say n is 4, we have three simple transpositions. The corresponding Dinkin diagram, we call these transpositions S, T, and U. So rather than writing the letters S, T, and U all the time, I'll be indicating them with the colors. So S will be red, T will be blue, and U will be green. So an object of this diagrammatic Soergel category is just a sequence of colors. So in the case n equals 4, we might indicate an object of the category by writing a couple of reds, and a blue here and there, and maybe some greens. And this formal sequence of colors is supposed to be thought of as an object of the diagrammatic category of circle bimodules. And then if you prefer not to draw colors all the time, you can write it this way. Okay, so I've just told you what are objects in the category. Now I have to tell you what are morphisms in the category. So morphisms. So a morphism between two kind of color sequences is supposed to be thought of as a linear combination of, here I'll take rational numbers to be my coefficients. So let's say Q linear combinations of diagrams, planar diagrams, you think of the bottom boundary, just like before, the bottom boundary will be thought of as the domain. The top boundary will be thought of as the codomain. And you look at all diagrams that can be constructed from the following pictures. So you have the one color generators, which are funny diagrams of this flavor. We have the two color generators, anyway, so the precise details of these diagrammatics are not entirely that important for us right now. But I just want to say, so the morphisms in this category are sort of generated by they're diagrams that can be obtained from these by gluing these diagrams together, mod a bunch of relations, modulo some number of relations. Okay, and I really don't want to go into what the relations are at the moment. Sorry. I'd like to not run out of time entirely. Okay, so the relevant fact for us is, so the tensor product in this category is obtained by placing diagrams side by side. So if you have a diagram F that represents some morphism in this category, and a diagram G which represents some other morphism in this category, their tensor product is just given by horizontal concatenation. So you just place the diagram side by side, and this is the sort of tensor product in this category. Sorry for the sloppiness of the picture. So this is not an additive category quite yet. It's a linear category in the sense that morphism spaces are linear, but you can formally adjoin all direct sums. And what you get is a category whose growth in T group is an integral form anyway of the Heck algebra. Okay. So any construction which could be performed in the world of Heck algebras, you can ask, does it have an analog in the world of zero bimodules? For example, this procedure of taking Hochschild homology or relative Hochschild homology, does it have an analog in the world of circle bimodules? And can I interpret these sort of skein theoretic operators that I defined a moment ago in terms of circle bimodules? The answer is yes. Okay. So to obtain a categorical analog of these of this Carlsson-Mellit algebra, we need a few basic ingredients. So to obtain the categorical analog of d plus d minus and yi and ti, what we need, so there's a few basic ingredients. So first off, we need to be able to, so the categorical analog of these generators Ti are provided by Rouquier complexes. the categorical analog of Hochschild homology is given by some DG version of horizontal trace, relative DG horizontal trace. So this is one of them, technically the heaviest part of the construction. It's a relative version of some DG horizontal trace of SBim. We need a categorical notion of these symmetrizers. And that's pretty much it. Okay, so okay, can I ask? Sorry, do I end on the hour? Or
we started a bit late, so yeah, you can end on the hour. We'll just have to cut some of the questions a bit short, but we do have a short break before the next talk, so that's okay.
I see. Okay, so okay, so let me kind of streamline this somewhat. So I'd like to, the most interesting part of this construction is how do we actually in the end interpret the pictures? So this process of identifying, like doing edge identifications in the rectangle, the role of that is played by this relative horizontal trace. So let me actually spend some time talking about what I mean by this, because it's the sort of most new ingredient of the story. So to obtain a categorical analog, of this vector space V and M, maybe I'll start with V and M tilde. This was the, in the world of Heck algebras, this was the span of all diagrams where we just connect up the rightmost M strands. Mod relations. And we don't necessarily symmetrize in the bottom. What we need is a relative version of this horizontal trace. So we need this, what I highlighted up here. Okay. So roughly what this is, okay, sorry, I'm feeling the time crunch here, but so we think of this category of Soergel bimodules, or its diagrammatic version, as a bimodule. So just like in the category, just like in this in the world of Heck algebras, we want to consider this guy as a bimodule for the two categories dm acting on the left and on the right. So for example, I mean, so this is a bimodule just by tensor product. So given I'm sorry. What I want to say is that dm can be thought of as a subcategory of dn plus m, where just like in the symmetric group or the Heck algebra, we kind of identify it with the stabilizer of the numbers 1 up to n. And so this makes this category into a bimodule category. For dm. And we would like to identify the left and the right actions of dm on dn plus m. So the first naive approach to what this means is, instead of drawing our diagrams in a rectangle, we will draw our diagrams in a rectangle with edge identifications, similar to what we did before. So here, because I'm drawing my diagrams, I suppose sort of, I have three directions in which to kind of glue diagrams now. I have the tensor product direction, which here corresponds to horizontal concatenation. I have the composition of morphisms direction, which is gluing diagrams vertically. But then there's this sort of third direction, which corresponds to how does Sn cross Sm sit inside Sn plus m. Anyway, and so the diagrams are somewhat rotated from how they were drawn a moment ago. So the edge identifications that I do here, since I want to identify left tensor product with right tensor product, the most naive thing to do is to draw the Elias-Kavanagh diagrams not in a rectangle, but to draw them in a cylinder. So the naive approach is to define the following category. Maybe for now I'll just call it D tilde N M. And this is the category with the same objects as Dn plus M, but the morphisms will be Elias-Kavanagh diagrams drawn in the cylinder, so the rectangle with edge identification. So still you have the top boundary, which can be the top and the bottom boundary are just arbitrary objects in this category. And now you identify this edge with that edge with the one caveat. So you draw some kind of crazy, possibly crazy Elias-Williamson diagram here. This picture is uncolored, I'm sorry. You allow your diagram to kind of run around the back of the cylinder. But the one caveat is that you're only supposed to allow, you are only supposed to allow these colors to be, so you restrict these guys to live inside the copy of SM. Sorry, what do I want to say? So for example, maybe the example probably speaks much better than anything else. So if we take N and M to both be 2, we can consider morphism. So given any sequence let's say so this is a perfectly well-defined morphism in this is a perfectly well-defined diagram. Oh crap. Let me write. Okay, so here I've drawn an Elias-Kavanagh diagram in the rectangle with edge identifications. But the important thing is I only allow, so the stuff that touches this sort of seam of the rectangle is sort of forced to live in the parabolic subgroup corresponding to dm. So in this case, we have the three simple reflections S, T, and U. And the only thing that I allow to touch the side of the rectangle is U. So this is how I define the sort of naive version of Hochschild homology. Sorry, this took a little bit longer than I intended. But so this is the naive approach is to define a category. So I kind of identifying the left and right multiplication of objects in DM corresponds to drawing Elias-Kovanov diagrams in this cylinder, but where morphisms in DM are allowed to pass from, they're allowed to hit the back of the rectangle. Goodness. And I should just say that there is a DG version of this construction, which is a derived version of this construction. So this gives our actual categorical version of the vector space VMN tilde and so by combining this with other ingredients like the categorified symmetrizer, so there's one subtlety in the story, which is that there's these. Okay, I shouldn't say very much more. I'm sorry. So you have to combine these with the other ingredients. So there's categorified symmetrizers that that we know how to construct. There's the Rouquier complexes, which give us analogues of braids, and by combining all these ingredients, you get a categorical version of these vector spaces V, and by literally just drawing the same pictures and interpreting them in terms of this DG trace, you get categorical versions of these operators, the Carlsson-Mellit algebra. And I'm sorry that it went over time and kind of ran out of time, but I'm happy to say more if you guys would like to. So I haven't yet actually drawn pictures, although if you've seen Nicolle give a talk, then you've probably seen them. I haven't yet drawn pictures for things like D plus star. So if you are curious what these things look like, please ask me. I should stop there.
Great. Thanks, Matt, for your talk. It's pretty cool seeing all these pictures being drawn, lots of loops going all around. So yeah, we have time for maybe one or two reasonably quick questions or requests for more elucidation.
Mm-hmm.
So at this point, I might ask, for the categorified symmetrizers.
Yes.
So I can see how you can add up, a bunch of Rouquier complexes together.
Yes.
To come up with something like the sum of a bunch of elements of your Peck algebra. Is the division by n factorial or the quantum factorial thing a routine thing?
I don't know if I don't know. Okay. Yeah, what a question. So that's, how do you actually construct the symmetrizer? And it's not really given by just a direct sum of Rouquier complexes divided by n factorial.
Okay.
There's like a handful of ways I know of how to construct the symmetrizer. So like my favorite way of constructing the symmetrizer is the following. But there's one thing that it is the most difficult thing to see, which is, I ran out of time to really discuss this. The most difficult thing to see is, what does this linear relation look like? I mean, constructing the symmetrizer is one thing, or categorifying it anyway is one thing, but like, what is this linear relation that, that relates P, the symmetrizer in n strands, with the symmetrizer in n minus 1 strands? What does it look like? And that's much harder to see. But if your goal is to construct the symmetrizer, then the following works just fine. This is my favorite construction. So it's an infinite complex, sadly. I mean, or not sadly, but you can't. Dividing by n factorial, quantum n factorial sort of necessitates like,
power series.
Yeah, power series, exactly. And so what you do is you put the monodal identity on the far right. You take the direct sum of all symbol transpositions, the bimodules corresponding to those, in the next kind of, so it's an infinite complex. So it looks like some sort of bar complex.
Yeah. Yeah, okay.
Okay, so you take the direct sum, and in the ith position, you see the direct sum of all possible Bott-Samuelsons of length I. And in the rth position, you see the direct sum of all possible Bott-Samuelson bimodules of length r. And then the map here is an alternating sum of lollipop morphisms. So this constructs for you the symmetrizer. But to see the relation, the sort of linear relation that you need is much more difficult, and I don't have time to. So roughly where the linear relation comes from is actually this categorical diagonalization story. So what you have to prove, so essentially where the linear relation comes from is
the full twist stuff that you've done with Ben.
yeah. So really what you're after, well, one version of the linear relation that we're looking for is really a linear relation between such a picture, anyway, between these three sorts of pictures. And the linear relation, when you categorify, the linear relation becomes a certain exact triangle. And if you were to try to recreate this linear relation at the categorical level, you would start with the kind of relation that comes from diagonal, like categorical diagonalization, and then manipulate that somewhat. So I can say more. I'm happy to, but I don't think now.
We'll delay that.
Yeah. I don't think now is the time for that. So.
Okay. Yeah. Thanks again, Matt. And yeah. We
All
should
right. Yeah.
probably,
Thanks, guys.